Welcome to Calc Chats 10. Today we're going to be talking about convergence using the nth term test and the direct comparison test. So something we want to go over quick is convergence and divergence. So convergence, we said the sum of a series approaches a number, it gets really close to a number. And divergence, the sum of a series never reaches a number, or it increases or decreases without bound. So for convergence, again, we're almost approaching like a limit. The sum it gets really close to a number, but it never goes over. Versus divergence, it just kind of goes with no control. It either increases or decreases without control. We talked about the criteria for convergence for these special series. So just kind of a reminder, geometric converges when R, the absolute value of R is less than 1, and it diverges when the absolute value of R is greater than 1. And for P-series, it converges if P is greater than 1, and it diverges if P is less than or equal to 1. And along with this is harmonic, and so harmonic, since that's when our P-series is equal to 1, it always diverges. So these are kind of criteria for special series that we talked about last time. But we're going to be getting into more diverse series, and they're not going to fall into necessarily one of these specific categories. And so we're going to try to use different types of tests to determine if a series can converge or diverge, and also considering the series that we already know, including P-series and geometric. So first thing we're going to look at is the nth term test. So this basically says any series, a sub n, diverges if the limit as n approaches infinity of a of n fails to exist or does not equal 0. Sorry, I should say limit as n approaches infinity of a of n fails to exist or is not equal to 0. So basically what this is saying is if my terms aren't getting smaller, my series is going to diverge no matter what. And so an example of this would be if I'm looking at the series n equals 1 to infinity of, let's just say the series 9 to the n plus 1. So we know this is a geometric series. We know that 9 is our ratio, and since it's greater than 1, it's going to diverge. But let's use the limit test to kind of look at our terms. So the limit as n approaches infinity of 9 to the n plus 1, well, when I kind of think about this function, if I plug in infinity, I use quotes, air quotes, plug in infinity, I'm going to get something that looks like 9 to the, infinity power. And this is just really big. And so our limit as n approaches infinity of 9 to the n power, it does not exist. And so that's how we know that this series is going to diverge. So we say this series diverges. So an example, this doesn't really cover convergence. An example of a series that diverges but passes the limit test, a very easy example is the harmonic series. So n equals 1 to infinity of 1 over n. If I take that limit, n approaches infinity of 1 over n, that goes to 0. So this passes the nth term test, but it still converges. So this does not test for convergence. This only tests for divergence. So we have to be absolutely sure that our terms are not going to 0 in order for it to diverge. If we run across a series like the harmonic series where it passes this test, we have to use other tests in order to prove it either diverges or converges. So our second test is called the direct comparison test. And this has a kind of like a long definition. And so we're going to let sum of an be a series with no negative terms. And so this is very important. I can't have any negative terms in my series. So no negative terms. One of two things happens. So AN converges if there is another convergent series. And we're going to call this convergent series C of n. And this is very important with A sub n, with AN less than or equal to C of n. So what this means is all of my terms in my A sub n sequence are less than the terms in my C sub n sequence. So either that happens, so AN converges if I can show that all the terms are less than my convergent series, or AN diverges if there is a divergent series we're going to call that series D of n, and this has non-negative terms as well. Write this on the bottom. So of non-negative terms. And this has our series A of n. All of those terms are greater than my divergent series. So basically, if I have a convergent series that I can compare my series to, all my terms in my series must be less than that convergent series, or if I want to show that it diverges, I can show that all the terms are greater than a given divergent series. So we're going to see an example of how this plays out because it's kind of hard to visualize right now when it's so abstract. So I'm given this series 1 over 3 to the n plus n. And I want to show that the series either converges or diverges. So I'm going to try to use the direct comparison test because I noticed that this looks similar to the series 1 over 3 to the n, which I can rewrite as 1n to the 3 to the n, which is also 1/3 n, and this is a geometric series with r equal to 1/3. So I can kind of notice that those two look alike. And the reason I can use this 1 to the n is 1 to the anything is just 1. So that's how I can kind of rewrite it into my geometric terms. So I know that this series 1/3 to the n power, that converges, and so what I'm going to try to do is prove every term in my new series is less than that term in my convergent series. And so I'm going to start first by just kind of listing out the terms of my new sequence. So 3 to the 1 plus 1, 1 over 3 squared plus 2, 1 over 3 cubed plus 3, 1 over 3 to the 4th plus 4, 1 over 3 to the 5th plus 5, and dot, dot, dot. And so when I use infinite series, I do want to put in that kind of dot, 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 because it keeps going. For infinite series, it doesn't stop. So let's calculate these really quick. And so I just used my calculator real quick to calculate these, but I got 1/4, 1/11, 1/30, 1/85, 1/248, and dot, dot, dot. So if I look at the terms for the series that I'm trying to prove it's less than, so 1 over 3n, let's look at those terms. And I'm going to write these in blue so we can kind of tell the difference. So 1 over 3 to the 1, 1 over 3 squared, 1 over 3 cubed, 1 over 3 to the 4th, 1 over 3 to the 5th. And so if we calculate these, oh my goodness, fast, we can see, if it'll let me go down, there we go. We can see that this is 1 over 3, 1 over 9, 1 over 27, 1 over 81, 1 over 243. And so when I look at my terms, I notice that 1/4 is definitely less than 1/3. 1/4 is a smaller fraction. 1/11 is less than 1/9. 1/30 is less than 1/27. And if I keep going, I'm going to see that all my terms in 1/3 to the n plus n are less than all the terms of 1/3 to the n. And so I'm going to say that the series n equals 1 to infinity of 1/3 to the n plus n is less than or equal to the series from n equals 1 to infinity, 1/3n. And so this series converges by the direct comparison test. And it's important that I say that because we do have different types of tests, as we just saw, the nth term tests that can prove a series diverges, and so this direct comparison test proved that this series converged. So this is it for convergence for now. Again, we're going to have even more tests to use. These are the first 2 of many that we're going to use. So please make sure that you come to class with any questions that you have about convergence or these 2 tests, and be sure to like and subscribe. Thank you so much for watching.